Okay, good morning. So let us start the lesson. So I will switch the topic to this a new one. It is called division algorithm in number theory. It's also very simple idea, but it's important in actually one of the fundamental theorems in number theories. I just want to describe the content of the theorem without having to go through the proof, because the proof needs something more advanced. But the idea is very, very simple. So let me just write the theorem for you first. So theorem, the division algorithm. So probably it's good to have this there here as well, okay? So let a and b be integers. So let me write b not equal to 0. Let a and b not equal to 0. For a, I don't have any problems with being at 0, but for b, I am demanding that it is not 0. So b integers, then there exists integers unique. Let me write unique integers q and r such that a is equal to b times q plus r, and this is happening. R is between, it's greater than or equal to 0, and is strictly smaller than the absolute value of b. So that's the content of the division algorithm. Yeah, but the idea is very, very simple. For example, if I give you a to be 20, so let us make it 21, and let me make b to be, say, 5. So what does it mean geometrically? It means that if you draw this real axis, and then this is the origin, for example, 0 here, and then a is here 21, and then b is, for example, around here, so I don't know, this is 5. So this is your a, this is your b. Sorry. So this theorem claims that you can find another integer q so that you can actually take this length. So for example here, how many of these lengths I can fit into this distance without passing 21? It's, yeah, 4 of them. And of course 4 is not the exact value because there is something remained, and that's called the remainder, which will play the role of r here. So in this case, I can take 4 of these lengths and then put them next to each other, but my restriction is that I'm not allowed to pass this 21. Either I should be exactly on 21 or before that. Okay, of course it is clear if I take 2 of them, I am still before that, but I want to fit as much as possible inside, as much as possible of these lengths inside this length, so that I become as close as possible to 21. But I can be on 21, but I'm not allowed to pass it. So that's the meaning of the content of this theorem. So it's clear. And that number q here, as you said, is how much I can fit 4 of them, but this will not exactly fill up this gap. So one thing is, one unit is the remainder. So that is what is happening. Yes, and this theorem guarantees that this is always the case. If you give me 2 numbers, a and b, so that the second number is not 0, I can always find unique integers with that properties. Yes? So in this case, if you see 21, which is A, is equal to B, which is 5, multiplied by Q, which is 4, and then plus 1. Okay? So, by the way, there are some names. Let me write them here. So if I write A equals to BQ plus R, and it is extremely important, you have to respect this. R should be somewhere between 0 and absolute value of B. If this is satisfied, then what you call this one is called the dividend. This is called the dividend, and this is called the divisor, and this is called the quotient. I think I misspelled that, yes. Quotient, and then this is the remainder. Yes? So these are the names that you need to know. Okay, but the numbers, the number R and the number B should satisfy this. Then you're allowed to call them these numbers. What do I mean by that? Because here, in principle, I can write 21. Instead of multiplying by 4, I can multiply it by 3. It becomes 15. And then to fill up this gap, I have to add 6. So you see that is this one has also the same structure here, yes? This is A, this is B, this is Q, this is R. But this Q and R are not perfect because I have to respect this rule as well. So you see here, R is 6, but B is 5. 6 is not between 0 and 5. So even though this is a true equality, but I will not call 3 the quotient and 6 the remainder, because these numbers are not satisfying this condition. Yes? But if in this case I can call this one to be the quotient and this one to be the remainder. Why? Because if you see this remainder R satisfies this condition because R in this case is 1, and it is really between 0 and absolute value of B, which is 5. So this is a true statement. So if I ask you what are the quotients and remainders of the division of 21 by 5, you should say 4 and 1. You are not allowed to say 3 and 6, even though for both of them this equality is true. Is that clear? That's the convention. So to practice this one, let me also give you some examples. In each case, determine the quotient and the remainder of A by B. Yes? It's actually a simple example, but I would say it is necessary. So I would write some parts for you. 1, 2, 3, 4, 6. Okay, so A23, B is 5. Here A is 28. B is minus 6. A is minus 31. B is 7. A is minus 25. B is minus 3. And then finally A is so I missed one, I think. 23, 28, minus 31, minus 25, minus 15, yes. And then B is minus 3 again. And then finally A is 5, B is 17, yes. So they have discussed this in your book. So what you need to know is that if I give you a pair of integers and I ask you what is the remainder and the quotient of some division, you should be able to answer this question. It's extremely simple. If both of them are positive, it might be a little bit, you need to be careful a little bit if one of these numbers or both of them are negative. So what you need to be careful about is that you not only have to respect this kind of equality for A equals to BQ plus R, but the numbers that you present as Q and R, of course, as far as you only think about R, and R should satisfy this relation. In that case, and only in that case, you are allowed to call that R the remainder. And then automatically, if you respect this, then you will get a unique value for Q. Then you can call that Q the quotient. Yes? So for example, here, if I ask you to do this, everyone knows that in this case, 23 can be written as how much? 5 multiplied by 4 plus 3. But you need to express, and this number that I presented here, 3, is really greater than or equal to 0 and less than absolute value of this B, which is 5. Yes? Because this and that are simultaneously satisfied, then you can say that yes, the quotient is how much is 4 and the remainder is 3. Yes? So for example, in this case, so what do you guess? What will play the role of Q and what will play the role of R? Yes?
R should be 4 and Q should be 4.
Let us check. So what you are supposed to write, you have to write 28 equals to minus 6, which is your B, multiplied by Q plus an appropriate R. Yes? So what is your suggestion again for Q? Minus 4. So it becomes 20. Okay, so if you choose minus 4, and then this becomes how much? 24. And then how much you need more? 4. Okay? So, and I think it's correct, yes? So what you need to do, so you say that this is multiplied by that plus 4. But this 4 should satisfy which condition? It should be greater than or equal to 0, which in this case it is true. And it should also be smaller than absolute value of B. But B is minus 6 here. But absolute value of minus 6 is 6, and 4 is indeed between 0 and 6. So that is true, and this is also true. So what you suggested is correct. So here in this case, Q is a negative number, but remainder cannot, of course, be negative. The lowest value for a remainder is 0. In this case, Q is minus 4, and R is 4. Yes, is that understandable? Okay, I just pause 2 minutes so that you can do the rest yourself, and then I can come back and solve it together. Okay, so let us try to solve it together. So here, A is minus 31 and B is 7. So what should I do here? Do you have your numbers? So I have to write minus 31 is equal to 7. Okay, now what should I write? Yes?
Times negative 5 plus 4.
Yeah, that is good. So you have to do it by negative 5, because The impression is that, okay, usually you might write -4 first, but that's not going to work, because if I write -4, then that's multiplied by this one, it becomes -28. But I want to reach to -31. I can do this only if I have the remainder to be -3. So that is true. I'm not saying it's wrong. But the point is that this number does not satisfy that condition that I need. So in this case, I cannot call this to be the quotient and this to be the remainder, even though this equality is true. So I have to find a way out of it, and what actually Gustav mentioned is correct. So instead of multiplying by -4, which is probably the natural choice first, you have to remember that in this case you have to multiply by -5, and then what happens, it becomes -35, but you have to go back to -31 by adding +4. But is +4 acceptable here? I have to check. I have to check what? I have to check that, is it true that 4 is between 0 and absolute value of 7? The answer to this part is yes. So this means that indeed Q is -5 and R is 4. So be careful. If you want to respect this condition, you will only get one answer for Q and one answer for R, and this is guaranteed by this theorem. It is not trivial, but it is the case. So if you respect that condition, everyone should find the same number for Q and the same number for R. But if you do not respect that one, of course, you have infinitely many choices for Q and R. Yes, tell me, is that understandable for everyone? Okay, so we now go to the next one. So what is this one here? I have to write -25, and then I have -3 here. So what should I do? I multiply by which Q and add which R to it, so that I come back to here and I also respect that extra condition. If I multiply by 8, it becomes -24, yes? And then what should I do? Plus, not +1, because I want to go to -24. So I have to plus -1, which is not acceptable. So then what happens? I multiply by what? 9. Let us work this one. So that's good, because -3 times 9 is how much? Is -27. But I am 2 units ahead before that, so I have to come back by adding 2 units to it. Are these numbers acceptable in this case? Yes. Why? Because I take 2. Is it greater than or equal to 0? Yes. Is it smaller than absolute value of b? Absolute value of -3 in this case. But absolute value of -3 is 3. So really 2 is between 0 and 3. So that is true. So then I would say that Q here is 9 and R here is 2. Yes? So what about number 5? A is -15. Yes, I have to write B, which is -3, so I'm waiting for you. What is Q and what is R in this case? Anyone else? Yes, Sarah? Yes, Q is 5, and what about R? 0. Yes, because then you need to see that 0 is greater than or equal to 0, which is true, and it is also smaller than absolute value of -3. So this is a true statement, and this is also true. So then you would say that Q is how much? Is 5, R is 0. What about number 6? Again, be careful. In the question, I have asked you the remainder of the division A by B. So I am not asking the bigger one divided by the smaller one. I'm asking A by B. So I have to put A on the left and then B on the right, and then I wait for you to give me Q and R. So what is Q and what is R here? Yes, Abdullah? Yes. So I mean Q is 0 and R is 5. And then is 5 acceptable? Yes, because 5 is greater than or equal to 0, and it is smaller than absolute value of 17. So that is true. So then Q is 0, R is 5. So if you are dividing a positive number by a positive number bigger than that number, then the quotient is 0 and the remainder is always the smaller number, so that you can have it in your mind. Okay, but that's the content of this theorem. But let us solve more exciting problems a little bit, because it's not that interesting now. Okay, so let me just write the summary here. So if A is equal to B, so if A, an integer, is equal to a non-zero integer multiplied by Q plus R, and R is greater than or equal to 0 and is smaller than absolute value of B, then you can conclude, if you want to, you can say that Q and R are the quotient. So I think I misspelled. So this is the correct way of spelling quotient, yes?
Yes.
So I don't know why I changed that. So this is correct. Quotient. So Q and R are the quotient and remainder of the division of A by B respectively, yes? So that was my mistake. I realized something is going wrong anyway. That the spelling is wrong. So this is the correct spelling. So something that we want to understand is just, I want to give you some examples, a little bit more interesting examples that you can use this idea. Yes? Okay, so for example, if the remainder of the division of A, I always mean integers, okay? So I don't need to emphasize in number theory. A by 12 is 10. What is the remainder of the division of A by 6? So let me read it this. If the remainder of the division of A by 12 is 10, what is the remainder of the division of the same A but by 6? Yes? Of course, in these questions, you can probably give an example in your head. So can you just give me can you just find the answer with some example? Of course, that example is not the solution, but it is actually good to understand the problem. For example, I take A to be 58. Yes? If I take A to be 58, for example, if I divide it by 12, what is the remainder? What is that? It's 10, yes? Because 4 times 12 it becomes 48. I want to reach to 58, so I have to add 10. 10 is the remainder. Now, I take 58 and now divide it by 6 instead. What will be the remainder? So practicing your multiplication table. No. 9 times 6 is 54. So 4. So it should be 4. And then I don't know, we can check other numbers. So apparently the number should be 4. But let us understand it from mathematical point of view. For any number a with the property that if you divide it by 12, it gives you 10 as a remainder. As the remainder. Okay, so how should I solve the problem? I need to translate this part of the problem in mathematical language. So what you say that the remainder of the division of a by 12 is 10. What does it mean? It means that this number a can be written as 12 times q plus 10. Yes? So if you want, you can say that there exists a q in z, if you want to write it really precisely, such that this number is 12 times q plus 10. And then you see that in the problem they have respected that 10 can be indeed the remainder because it is greater than equal to 0 and it is smaller than 12. So that's okay. Okay, now I want to say something about the division of a by 6 instead. So in the scratch work, so you need to have this combination. You need to have a here and you need to have 6 times some q plus some r. Yes, that is your goal. Because you want to talk about the remainder of the division a by 6. So you need to divide a by 6, you get some quotient, you get some remainder. They are not asking about the quotient, understandably, because quotient could be a lot of numbers. There are infinitely many answers. They're asking about the remainder. Okay, what can I do? For example, one idea comes to mind is to make this 6 appearing here. Yes, so I would write a, instead of this I would write 6, and then I would write 2q plus 10. Yes, and can I give this a name q here? And then I will have that combination a is equal to 6q plus 10. Do you think the problem is done? Can I say that still the remainder is 10? Why not? Do you understand what I did? Instead of 12q, I wrote 6 times 2 times q. And if q is an integer, definitely 2 times q is also an integer. So that's correct. I give it a new name, capital Q. And then I see that this a is 6 times an integer plus 10. Okay? Can I conclude that, okay, 10 is again the remainder? Why not? Because this 10 does not satisfy the appropriate condition. 10 is, if 10 is going to play the role of the remainder, it should be greater than or equal to 0, which is correct, but should also be smaller than absolute value of this number 6, which is incorrect. So this means that even though what I have written here is completely correct, my conclusion that 10 is the remainder is not valid. So what do I have to do? So this means that this part is good, but I have to do something with this 10 right now. So now can you tell me what to do? So I would write a equals to 12q. So I can write it as, yes, I can write it as 12q. Instead of 10, I write 6 plus 4. Yes, and then what I do, I factor a 6 out. You see, I have my strategy. I want to have 6 here. So using this idea, I take 6 out, and 2q plus 1 is left. Yes, and then 4 is here. Now, q is an integer, so 2q plus 1 is also an integer, so I can call it a capital Q. And then I will have a is equal to 6 times an integer, which I don't know exactly. The reason is that I don't know q yet, so I don't know the capital Q, but I don't care because the problem is asking about the remainder. But what is left here is 4. Now, can I conclude that the remainder is 4? Yes. Why? Because you need to write that 4 is greater than or equal to 0 and is smaller than absolute value of this number, which is 6. So therefore, the remainder that is asked in the problem is 4. And that was correct. Do you remember? When I divide 58 by 6, I got the remainder to be 4. So what we have shown rigorously, it is like this. It doesn't matter which number I choose. As soon as this number divided by 12 has remainder 10, if I take that number and divide it by 6, the remainder becomes definitely 4. Yes? Okay, now I will write an example, and I want to wait for you, because again, the idea is clear. You have to practice to understand how to solve harder problems. So what I write here, so example. The remainders of the divisions of A and B by 19 are 3 and 17 respectively. What is the remainder of the division of 2a minus b by 19? Okay, so if you can solve this problem on your own, so it means that you actually understood everything is going on. But of course, some of these problems could be hard. I will give you more examples. But I mean, if you can solve this problem on your own and find the correct answer, it means that you really understood the content of this division algorithm. So I want to wait for you a little bit